The principle of the modern anesthetic machine is that it is a partial rebreathing system. And what that means is that when the patient inspires oxygen, air, and anesthetic vapor, they don't use all of it. And in fact, as far as oxygen is concerned, it's said that the average 70 kilogram individual burns about 200 milliliters of oxygen a minute. So all we in theory have to do is deliver 200 milliliters of oxygen to the patient every minute. The only thing the patient does in response to this is produces carbon dioxide. We can't allow the patient to rebreathe the carbon dioxide because that would result in the respiratory acidosis we talked about earlier, would cause tremendous stimulation to ventilation, and in fact would make it almost impossible to safely anesthetize the patient. So we have to scrub the carbon dioxide out of the expired gases. And we do this by using soda lime canisters. And you can see on this machine, the two devices that are piled one on top of the other are soda lime canisters. And fresh gas flow comes in from the bottom. Expired gas comes from the bag in the lower part of the diagram. And then as the bag is compressed, a combination of fresh gas and expired gas is forced up through the exchange material, and carbon dioxide is scrubbed out so that the material going to the patient is free of carbon dioxide. It has vapor in it. It has additional oxygen because most of us try to compensate for that 200 mils of oxygen that the average patient burns every minute by giving them something more than 200 mils. I, on average, give 400 mils at least per minute in a patient who's not otherwise requiring extra oxygen. So there's a safety margin that we all work with. The benefit of this kind of a system is that we don't waste a lot of materials. So patients expire unused vapor and inspire it again, which allows them to continue to remain anesthetized, even rebreathing the same anesthetic vapor repeatedly. They get rid of carbon dioxide with every breath, and they get new oxygen with every breath. The overall waste of gas is very low. So we're not venting gas to the vapor or to the atmosphere, particularly seeing that vapors do have some environmental risks associated with them. And we're also maintaining cost effectiveness by reducing the amount of vapor that we use overall. So the soda lime canister, as I mentioned, scrubs the carbon dioxide out of the expired gas. So the expired gas on this slide is blue, and the fresh gas flow is red. So that fresh gas flow will consist of new vapor and oxygen and perhaps some air. The expired gas will consist of unused vapor, some unused oxygen, and carbon dioxide. All the gases go through the soda lime canisters, the carbon dioxide is removed, and everything else goes back to the patient. So soda lime consists of calcium hydroxide, about 75%, and water about 20%, sodium hydroxide about 3%, and potassium hydroxide about 1%. It's an exothermic reaction so that when the gases pass through the soda lime, heat is generated, plus water is created so that in time, the soda lime becomes wet and warm, and as it becomes wetter and it absorbs more carbon dioxide, it becomes exhausted. And it has a color dye in it that changes color and warns the anesthesiologist that it's time to change the soda lime. So the overall reaction, as I mentioned, is carbon dioxide plus calcium hydroxide leads to the formation of calcium carbonate and water and heat. Water, calcium carbonate, and heat collect in the sodium lime. The colored dye in the sodium lime, which changes color when the material is exhausted and indicates it's time to replace the soda lime, shows up. The anesthesiologist hopefully notices it. And in addition to the sodium lime changing color, the expired gases are being monitored. So it's possible to see, and inspired gases, it's possible to see if carbon dioxide is building up in the circuit and the patient is rebreathing carbon dioxide, which is a situation we simply can't allow to happen. Barolime is the same substance basically as soda lime, except it uses barium hydroxide instead of calcium hydroxide in the granules. So similar systems exist in submarines, diving bells, and decompression chambers, but in nowhere near the finickiness that is apparent in the anesthetic machine. In those systems, they're just big blocks of barolime or soda lime, and they're periodically checked to see if they're getting exhausted, but there's no effort to control flow through them or to control the amount of gas they're engaged with. So the overall reaction is heat produced by the scrubbing of expired gases may be sufficient to cause partial breakdown of sevoflurane with the release of a substance called compound A, which can cause kidney damage in rats. We actually don't know if this is a problem in humans, but the recommended flow through an anesthetic machine when using Sevolime is 2 to 3 liters of fresh gas per minute to maintain lower temperatures in the soda lime. With desflurane, we can turn the total flow way down, and this actually results in desflurane being a very economic drug to use because we use so little of it per minute. Excess gases in the circuit are released through an adjustable valve mechanism and are scavenged to the outside atmosphere. As I already mentioned, there is some risk of environmental damage from vapors being scavenged in this way, so we try to keep the total amount being released into the atmosphere at a low level.